Hi, everybody. This is chapter 13, and we're doing the example problems from chapter 13. And I hope you all are doing well. Example 13.1. Wow, this is thick. I don't like that. Let me try to thin it down. Let's see. Try that. 13.1 is calculating gravitational force. Aw, that's like a crayon. Let's see. I'm going to try to change that. Kind of cute, though. Let me get my box of crayons out and get my pencil out. Let me see what I can do there. Come on now. Is it still thick? Wow, I don't even know what happened. But we'll deal with a thick pen today. Let me see if I can amend this. Can we get thinner? Nope. Don't know what happened, but we'll just deal with this. Anyway, it reads, the mass of one of the small spheres of a Cavendish balance is 0.0100 kg. So M1 equals 0.0100 kg. Oh, so thick. So strange. Come on now, do that. And the mass of the nearest large sphere is 0.500 kg. So M2 equals 0.500 kg. Fine. Okay. The center to center distance between them is 0.0500 meters. So D equals 0.0500 meters. And now it asks to find the gravitational force Fg on each sphere due to the other. So Fg is equal to G M1 M2 over D squared. And this is a constant. I really don't like that thick stuff, but anyway, it's a FG is going to equal to 6.67 times 10 to the negative 11 newtons meters squared over kg squared times 0.01 kg. I'm not going to put the other zeros there because it's so thick. I don't think I'm going to have the room. Let's see, do that. Times 0.50 kg divided by 0.0500 meters quantity squared. And what we're going to get here, the book has so graciously done it for us, is Fg equals 1.33 times 10 to the negative 10 newtons. Not much force. Okay, thank you. Going on to 13.2. 13.2, acceleration due to gravitational attraction. We're just going to do the same thing, F equals ma, but let's see what we have got going here. Suppose the two spheres in example 13 are placed with their centimeters 0.500 meters apart at a point in space far removed from all other bodies. What is the magnitude of the acceleration of each relative to an inertial? So F equals ma, so A is going to equal to F over m. So we have that value, so we'll do A1 and A2 is going to be equal to the force we got, 1.33 times 10 to the negative 10 newtons. And this is going to be equal to 1.33 times 10 to the negative 10 newtons. And we'll have this divided by the mass of the first guy, which was a 0.0100 kg. So 0.0100 kg. I'm kind of getting used to this thick crayon-like writing pen. So now we've got 1.33. That'd be 10 to the negative 12, or 10 to the negative 8, I'm sorry, times 10 to the negative 8 newtons. And this guy is going to be 2.66 times 10 to the negative 10. Oh, I'm sorry, this is in newtons. That's newtons divided by kilograms, which is going to be equal to meters over second squared. And that's also meters over second squared. It's a unit of acceleration. Yes, it's A. Okay, this is 13.3. It's superposition of gravitational forces. And we have a diagram. It says many stars belong to systems of two or more stars held together by their mutual gravitational attraction. Figure 13.5 shows a three-star system at an instant when the stars are at vertices of a 45-degree right triangle. Find the total gravitational force exerted on the small star by the two large ones. So what we've got here is, here's your diagram. It's got this guy, and the two large ones here, and then you've got your small guy here. And we know that this guy is, his mass is 8 times 10 to the 30th kg. And this guy is 8 times 10 to the 30th kg. So 8, 10 to the 30 kg. And we know this distance is 2 times 10 to the 12th meters right here. Yeah, that's 12. That's 12 right there. So, and this guy is 1 times 10 to the 30th kg. 1, 10 to the 30th kg. And you got a force going here and a force going there, and that's what we like to know. And then we're going to have some kind of vector sum, and that's our goal, to find that out. All right, I figured it out, so we're golden now. And we call this guy F1. Yeah, I figured it out. And this guy is F2. And obviously that is 45 degrees. Okay, so we're going to do F1. This is beautiful. Equals. This is F1 between, let's see, F1 is going to be between the 8 kilogram and that little guy. So we've got 8 times 10 to the 30 kg times 1 times 10 to the 30 kg. And I'm going to just go ahead and write G. And by the way, G is equal to 6.67. You should probably memorize this. Times 10 to the negative 11. A newton's meter squared over kilogram squared. So probably a good thing. It's a good value to memorize, kind of like 9.8. It's not that hard. All right. And this distance, are we given that distance? No, we're given this distance, and we're given this distance, and that's also 2 times 10 to the 12th meter. So we got to figure that out. So we're going to, that times G over the square root. Oh, no, it's squared anyway, so I can just, don't have to square root it. 2 times 10 to the 12th meters, and that's quantity squared, plus 2 times 10 to the 12th meters, and that's also quantity squared. And that is going to be equal to, wow, 6.67 times, this is equal to 6.67 times 10 to the 25th newtons. All right, for F2, it's going to be the same thing, right? No. No, F2 is only this. So it's not this hypotenuse guy. So F2 is going to be, can I just do, call this M1, M2, and M3. I'm going to do G times M1. Oh, wait, I should call this M2. I'll call this 3. Call that 3. This will just make more sense. M1, M2, M3. All right, so M1, M3 over 2 times 10 to the 12th meters, quantity squared. Right, why do I have this there and that there? Because I had to take that squared plus that squared equals the square root of that, but we squared it. Oh, I don't need 12 there. I just need 2. I don't know where that's just squared. Okay. And this value is going to equal 1.33 times 10 to the 26 newtons. Now I'm going to pause, erase my board, and continue. Okay, now we're just going to solve for the components and find out what we got going here. So F1 of x is going to equal to that magnitude, which is 6.67 times 10 to the 25 newtons times the cosine of 45. Right? This is F1. And F1 of y is going to be the same thing times the sine, 6.67 times 10 to the 25th newtons times the sine of 45. Okay, and for F2, we don't have a y component, so F1, 2 of x is just going to be that entire force, 1.33 times 10 to the 26 newtons, and F2 of y is going to be equal to 0. And then I guess I add them up and find their magnitude and direction. So let me go ahead and do that. Pause you and clear. All right, so f of x equals f1x plus f2x. And I'm going to go ahead with the book's numbers. I really trust them. That's going to equal 1.81 times 10 to the 26 newtons. And f of y equals f1 of y plus f2 of y. And that's going to be equal to 4.72 times 10 to the 25th newtons. And so now to get our magnitude and direction, F magnitude is going to be equal to Fx squared plus Fy squared, and that's equal to 1.87 times 10 to the 26 newtons. And theta is going to be equal to the tan inverse of f of y over f of x. And that value is going to be 14.6 degrees. And that's 13.3, you guys. Okay, we're doing example 13.4. It's called Gravity on Mars. It says a robotic lander with an Earth weight of 30 newtons is sent to Mars, which has a radius of Mars equals 3.39 times 10 to the 6 meters. And mass 6.42 times 10 to the 23rd kilograms. Find the weight of the lander on the Martian surface and the acceleration there due to gravity. All right, so first of all, we need to know the mass of that robotic lander. So we're going to do 3,430 divided by 9.8 meters per second squared. That is going to give us 350 kgs. All right, now we're good to go. All right, so we have G, so force of G on Mars equals G, and that's times M1, 350 kg, times M2, which is 3.39 times 10 to the 6 meters, divided by that distance. The distance from the robotic feet to its center of mass is trivial, so we're just going to use that Martian one.
times 3.39 times 10 to the 6 meters. And that's going to be quantity squared. And the book has kindly solved that for us. So FG on Mars equals, let's see, 1.3 times 10 to the third newtons. 1.3 times 10 to the third newtons. But that's not A. So to get A on Mars, we need A divided by that mass of the robot. So that's going to, I'm sorry, that's F on Mars. A on Mars equals F on Mars. So we're going to get 1.3 times 10 to the third newtons divided by 350 kgs is going to give us 3.7 meters per second squared. Oh, it would weigh so little on Mars. Anyway, that's 13.4. Very cool. All right, everybody, this is example 13.5, and it's called From Earth to the Moon. Wouldn't that be wonderful to go to the moon? Anyway, it reads, in Jules Verne 1865 story with this title, 3 men went to the moon in a shell fired from a giant cannon sunk in the earth in Florida. Is that ironic? He wrote it in 1865, and he had 3 guys like we had in our lunar mission going from Florida. So wow, he was he a prophet? Sounds like it, right? Anyway, I digress. Find the minimum muzzle speed needed to shoot a shell straight up to a height above the earth equal to the earth's radius RE. RE, so we want to do that. Find the and then find the minimum muzzle speed that would allow a shell to escape from the earth completely via escape velocity. So 1 is RE and 2 is escape velocity. And then let's see. And then it gives us some values. The Earth's radius and mass are RE equals 6.37 times 10 to the 6 meters. And ME equals 5.97. Well, you do these problems long enough, you know all these values, times 10 to the 24th kilograms. 10 to the 24th kg. All right, let's get started. Okay, so what we have here is we have the kinetic energy initial plus gravitational potential energy initial equals kinetic energy final plus gravitational potential energy final. So we have a 1/2 mv squared plus m. Oh, we're going to use that guy. Negative g, mass of the Earth, mass of the whatever rocket times radius of the Earth equals a negative g, mass of the Earth, mass of the rocket times 2 radius of Earth. So we're going to take this over here, and we're going to have 1/2 mv squared equals, it's going to be positive going over there. It's going to be 1/2 g, mass of the Earth, mass of the rocket over radius of the Earth. Okay, now we're going to just solve. We're going to get equal to v, and these guys will go, equals the square root, and these m's will cancel out as well, of g, mass of the Earth, radius of the Earth. And if you put all those values in that you got right there, you are going to get 7,910 meters per second. All right. And that's to get halfway up there. That's like the speed of a satellite about, right? Something like that. Anyway, let's continue. Now for the second part, we want escape velocity. So we got KE plus KE1 plus U1 equals 0, right? We don't want it, we want to shoot it far enough that it has no more potential energy with respect to the Earth, and it can peter out on that kinetic energy. So we have 1/2 mv squared minus g, mass of the earth, mass over radius of the earth. That's radius of the earth. Okay. Why isn't it squared? Because it's radius of the earth squared times the radius of the earth there. So that's why it's not squared. But anyway, so we're going to take these guys out. And we'll get 1/2 v squared equals g, mass of the earth, over radius of the earth. And we'll put a 2 there, and we'll go under the radical. That'll cross out, and that'll cross out. And that's what that'll equal. You fill in the numbers, and you get escape velocity is going to be 1.12 times 10 to the 4th meters per second. Which they do the conversion, that's about 25,000 miles per hour. Well, that's how hard you have to throw a baseball up in order for it never to come down again. 25,000 miles an hour. All right. Example 13.6 says a satellite orbit. You wish to put a 100-kilogram satellite into a circular orbit 300 kilometers above the Earth's surface. So we have 1,000 kg, 1,000 kg. And it's 300 kilometers, so 300 times 10 to the 3 meters. Let's just go ahead and do that. Above the Earth's surface. What speed, period, radial acceleration will it have? How much work must be done to the satellite to put it in orbit? How much additional work would have to be done to make the satellite escape Earth? The Earth's radius and mass are given in example 13.5. And the radius, if I recall, is 6.36 times 10 to the 6 meters. And the mass was equal to 5.27 times 10 to the 24th kg. All right. So let's see. We are going to have the velocity is going, if it's going to stay in orbit, the velocity is going to have to be equal to the force of gravity. So, I'm sorry, the centripetal force. V squared over R is going to have to be equal to M V squared. G M1, M2, mass of the Earth, over this radius of the Earth plus the height of the rocket. And that's quantity squared. So these m's are going to go. And this r is the same as that. So one of those will go with that. So v is going to be equal to the square root of g times the mass of the Earth times the whole distance from the center, which is going to be 6.36 times 10 to the 6 meters, plus, that would be 3 times 10 to the 5th meters. And v is going to be equal to, I'm going to use their value, 7730 meters per second. All right, and that's v. Now to find the orbital period, v is going to be equal to this orbital length, so 2 pi radius of the Earth plus a height above Earth, divided by t. And so t is the value we're looking for. So t is going to be equal to 2 pi 6.36 times 10 to the 6 meters plus 3 times 10 to the 5th meters. That's the circumference. And then that's over 7730 meters per second. We're going to get a value in seconds, which would be 5420 seconds. And if we divide, let's see, you can get that in minutes by 1 minute divided by 60 seconds. That will give you 90.4 minutes. Wow, they're fast. Well, that's fast. Okay. All right, now we want to find the radial acceleration, and a radial is defined as d squared over r. So what we're going to have here is 7730 meters per second. That will be quantity squared divided by r, which is a 6.36 times 10 to the 6 meters plus 5 times 10 to the 5th meters. And our value is going to be for that radial acceleration, 8.96 meters per second squared.
And that must be the gravity up there. So. Okay, for part, was this a C? D, no, it's B. B, we want to know how much work must be done to the satellite to put it in orbit. So from equation, I think it's 1313. Yeah. We have E equals negative 1/2 times G, M1, M2 over R. Okay, so we have, if you fill in that blank, we have equals G times the mass of the Earth, 5.97, 10 to the 24th kilograms, times the mass of the satellite is 10 to the 3rd kgs, divided by 2, and that's a negative, sorry, 2 times 6.67, 10 to the 6 meters. And we're going to get an answer of negative 2.98 times 10 to the 10th joules. A lot of joules. All right, pause and continue. Okay, now we want to figure out how much work is going to be required to make it escape the Earth's gravitational clutches. So that's going to be equal to the negative amount of potential energy it has on the surface of Earth. So that's going to be equal to the force times the radius, right? So that's going to be equal to the force times the distance is going to be G, M of the Earth, M of the satellite over R squared, radius of the Earth squared, times the radius of the Earth. This is its potential energy, so this is going to be equal to, if I do the math, it's going to be equal to G, 5.97 times 10 to the 24th kgs, times 10 to the 3rd kgs, that's the satellite, divided by 6.36 times 10 to the 6 kilograms. And that is going to be negative 6.25 times 10, 3.27 times 10 to the 10th joules. All right, this is example 13.8, Kepler's third law. And it says, the asteroid Pallas has an orbital period of 4.62 years. That's T. And an orbital eccentricity of 0.233. Find the semi-major axis of its orbit. Okay, so we have from equation 13.3, we've got the period T equals 2 pi. A, that's semi-major axis to the 2/3, and over the square root of G times M MS, mass of the sun, or whatever it's orbiting. Okay, so we have A
equals T times the square root of G mass of the sun divided by 2 pi, and this is to the power of 2/3. Okay, so I'm going to square both sides, or take everything to the power of 2/3. And I'm gonna get A equals G mass of the sun times T squared divided by 4 pi squared, and that's all going to be to the power of 1/3. And so that length is going to be 4.15 times 10 to the 11th meters. And that's directly from equation 13.17, Kepler's third law. All right, this is 1318. All right, and it states the asteroid Pallas has an orbital period of 4.62 years. Oh, I'm sorry. No, we already did 1318. We're doing 1319. My bad. For 1318, you have to look a lot of values up in the book, like the mass of the sun, and you convert that 4.62 to seconds. But anyway, well, let's move on. Comet Halley moves in an elongated elliptical orbit around the sun. Its distances from the sun at perihelion and aphelion are 8.75 times 10 to the 7th km and 5.26 times 10 to the 9th km. All right, find the orbital semi-major axis eccentricity and period. All right, so if you look at figure 1318, it shows you what the perihelion and the aphelion are. And then to find the that major axis, that's the sum of the two. So A equals 1/2 8.75 times 10 to the 7th km plus 5.26 times 10 to the 9th km. And A is going to equal 2. A equals 2.67. Ow! Oof, bugs biting me. 2.67 times 10 to the 9th km. Now, if you now we're supposed to find the eccentricity. So if you look at that figure 1318, you will see that the semi-major axis minus the eccentricity times the major axis equals A times 1 minus E. So we'll find out, we're just going to solve for E. E equals 1 minus 8.75 times 10 to the 7th kilometers divided by A. And that's going to be equal to 8.75 10 to the 7th km. 1 minus that over 2.67 times 10 to the 9th km, and you're going to get 0.967. Now to solve for the period, from equation 1317, you're given T equals 2 pi A to the 2/3 divided by square root of G, mass of the sun or whatever it's orbiting. So we're going to get 2 pi times 2.67 times 10 to the 12th meters to the 2/3 divided by the square root of G, I'm just going to use G, times the mass of the sun which is 1.99 times 10 to the 30th kgs.
All right, 1311 says astrophysical therapy suggests that a burnout star whose mass is at least 3 solar masses will collapse under its own gravity to form a black hole. If it does, what is the radius of the event horizon? Okay, so we're going to use equation 1330, which says the radius, it's called the Schwarzschild radius, is equal to 2g, mass of the black hole, that's a big M, divided by speed of light in a vacuum squared, c squared. So if we put in the numbers here, we're going to get equals 2. I'm just going to use g times 6 times 10 to the 30th kgs. Divided by 3 times 10 to the 8th meters per second, and that's quantity squared. And that's going to give us 8.9 times 10 to the 3rd meters. And that was 1311. And that's it for chapter 13.